Okay guys, you're going to have to bear with me a little in this particular lesson since I am starting to use a new screencasting tool, so my writing may be a little off, but this lesson is going to be the start of our Chapter 2, Information on the Chemistry of Life. So the first thing that we're really going to talk about is why exactly it is that we study biochemistry in A&P. And the really big thing that we want to focus on is the idea that it's all about cellular function, and the idea that the body depends on that chemical level for everything chemical to work in order for the body as a whole to work. So as those chemicals are changing, cellular functions are ultimately the result. So when we talk about what the cells perform, they're really chemical reactions that depend on the chemistry of the body, which is back up to that whole concept of biochemistry. All right, biochemistry, bio meaning life, chemistry being the chemical composition, the matter, the structure of matter. So we're really talking about that last bullet there, that chemistry deals with how we're composed and how those different composed matter, those atoms and elements, are going to be reacting with one another. So we want to talk about biochemistry, like I talked about, bio meaning life, so chemistry being biological chemistry, right? So we're talking about specifically chemistry in living things. And it's really important to use that biochemistry to figure out how exactly we use that process to improve medicine. We know that new drugs are dependent on understanding at a chemical level what the body is going through so that we can actually combat any diseases or disorders with drugs that can fix exactly what it is that's going wrong. We can also move on to talking about matter and defining the fact that matter is anything that has mass and takes up space. So matter is anything that's composed of elements. And when we say elements, what we should really know is that we're referring to the idea of the periodic, wow, bad handwriting, periodic table of elements. So we're talking about all those things that show up in the periodic table. And an element, what we're really talking about is a pure form of a substance. All right, so elements, we're really focusing on it being pure because we're only talking about it being made of one specific type of atom, one specific type of unit of matter. Right? So when we talk about the element being helium, right, helium is going to be only composed of helium atoms. Right? So when we talk about elements, we're talking about pure. Picture here showing us the periodic table, and what's really interesting is this particular periodic table recognizes exactly what the biological relevance of a lot of these elements are. So we're looking at hydrogen and carbon, nitrogen, oxygen, phosphorus, sulfur, all right, all of these, yellow being essential, being really important. And as we continue with this unit, you're going to recognize why it is that those particular elements are so important. And we often refer to those elements as schnapps. So, like I said, there are some elements that are more important than others. So bulk elements being what the body needs in large amounts, trace elements being needed in smaller amounts, and then the ultra trace, there are some things that your body requires in ever so slightly the littlest amounts, but when you start to increase the amounts, that particular element results in toxicity within the body. We can also talk about atomic structure when we're focusing on the biochemistry of living things and identifying that the nucleus being the center of an atom, just like the nucleus of a cell is really the center of the cell, and that nucleus is going to be made up of protons and neutrons. And we should know that those protons are going to be the positive ones, and the neutrons are going to be the neutral. So we should know that neutron, is neutral, and then electrons being the negative ones, and they're circling the nucleus. And electrons are really going to be what determine the reactivity of elements and whether or not it's going to be looking to bond with other substances or react with other substances. So So this is just a picture identifying atomic structure and pointing out that this whole entire area in the center is the nucleus. And you can see that we've got neutrons that have no charge versus protons that have a positive charge. And then circling around, we have these electrons with a negative charge that are following a path around the nucleus of the atom. Little table that just kind of sums it up, and even goes so far as to talk about ions and molecules, which we'll get to. So when you look at the periodic table, this particular picture that you see here should be relatively familiar. And it should be reviewed knowing that the atomic number is what's on the top, the symbols in the center. Often you can find the name, so like we have carbon here, listed beneath the symbol, and then the atomic mass, which is often a decimal point. So when we talk about atomic number, that top number is really about the number of protons. And that atomic number is unique. You can't change an atomic number without changing what element the actual atom is. So the other interesting thing is that atomic number is number of protons, but we typically assume, all right, so it's important to make sure that this last bullet, we know that this is an assumption. Sorry about my bad writing, guys. That says assume equals the number of electrons in the atom. And the reason that this is because we want positives, which is the protons, to equal our negatives. Because if we have 6 positives and 6 negatives, then we have an overall charge of 0 and we have a neutral atom. And a neutral atom is less reactive. Atomic weight is going to be protons plus neutrons, right? So if we have 6 protons, according to the atomic number in carbon, and we have an atomic mass of 12, we should know that protons is 6, and then protons plus neutrons is 12, which we can assume then that if protons is 6, neutrons should also be 6 to get our atomic mass to be 12. And it's also important to recognize that the reason that we don't really include electrons in this weight is because the electron's weight is so small, so minute, that it really doesn't contribute any significant weight to the atom itself. We can move on talking about ions. And ions is really talking about atoms with a charge. So an ion, atoms with a charge. All right? They have the same atomic number as the other atoms of that element and the same atomic weight, because like we said, we haven't changed protons or neutrons. The thing is that we gain or lose electrons. So a cation would be a positive, oops, there's supposed to be an I right there, guys, positive ion, right? This would be something, an atom that lost electrons. If it loses an electron, it loses a negative charge, which means that it should have more protons than electrons, which is going to give it a positive charge. Versus an anion, which is a negative ion, should have gained electrons because it's gaining a negative charge or more than one. And by gaining more negatives, overall, it's going to have a negative charge. And we typically write in the form of the atomic symbol with the charge superscripted. So for example, what I'm talking about is our atomic symbol for sodium. Then we would have that positive, all right, to indicate the overall charge. So the picture here depicts that in sodium, we've got one little lone electron floating in the outer orbit, and it's just easier for sodium to give up that electron, so we lose an electron and become positive, cation. So sodium becomes a positive charge. We also have something called isotopes when we talk about atoms. And if we look here, this is kind of replicating what it is that we see when we look on our periodic table. However, if we look over here, the atomic weight is slightly different. And that's because isotopes are atoms that have a different atomic weight. And we write these in the form of the element and the incorrect atomic weight. For example, we would write carbon dash, and that incorrect atomic weight is 14, so we would write carbon 14. And if it has an incorrect atomic weight, we know that that atomic number is our protons, and we know that the atomic weight is protons plus neutrons, so we can really deduce and figure out that that atomic weight is wrong because it has a different number of neutrons. So there's a different number of neutrons. Again, guys, forgive me for the bad handwriting. We can also talk about the stability or radioactivity of isotopes. So there are some stable isotopes that don't decompose, right? They're very stable on their own and exist perfectly fine. But then we have something called wow, lots of typos here. That's supposed to say radioactive isotopes. They have unstable nuclei, so they begin to break down. And as they break down, they're releasing energy, and that energy that we're really talking about is radiation. Hence the radioactive component. So examples, iodine or thallium, all right, which we use to detect and treat diseases. And as these radioactive isotopes are breaking down, because they're unstable in nature, as they break down, they release small or large amounts of radiation. So talking about that radiation, we have 3 different forms of radiation: alpha, beta, and gamma radiation. And these are those particles that are being given off as the isotope is decomposing. So like it says here, the particles that are released. When we talk about alpha radiation, all right, the thing to focus on is that this is heavy, slow moving, all right? It's not going to be able to penetrate. Versus beta radiation is going to be slightly smaller, faster moving, and it is going to be able to penetrate. And then gamma radiation is going to be the most penetrating. So we assume it's the smallest, fastest moving. And gamma radiation is really what's going to be able to penetrate through your body. So we're kind of going in, I guess, levels of danger, you could consider it, or concern. Alpha radiation being the least because it's not really going to be able to penetrate the matter, and the further along you get, the more penetrable it is going to be. We can also talk about radioactive decay in terms of the rate of how quickly it's decomposing and breaking down and giving off those particles, that radiation, in order for it to become stable. And the really interesting thing here is that as radioactive isotopes decay or break down, right, that initial atom that they are becomes something totally new. So for example, as a carbon isotope decomposes or decays, it becomes nitrogen. We can also talk about half-life when we talk about radioactive decay, and what we're focusing on half-life is a type of measurement that we use for radioactive decay. And half-life, maybe you've heard, for example, when we're talking about fossil dating or fossil records, right, we talk about the half-life of the isotopes that are in a particular sample of matter or a sample of fossil, because what we're doing is measuring the amount of time for half of the isotope to break down. So by taking a sample and measuring the amount of the isotope that's left or the amount of isotope that's remaining, we can determine exactly how much would have been there based on how long it takes for all these different isotopes to break down. And half-life is actually a set value. It's a set number that exists for the different isotopes, the different elements. So carbon breaks down in a certain amount of time, and based on a sample, you can kind of count back and figure out how long that sample has been there. So half-life is a method of measurement that we use using isotopes in science. This pretty much wraps it up for our lesson. If you guys have any questions, please feel free to see me.